Hey, welcome back. So this is more differential equations, in particular solutions, sort of by hand solutions to differential equations. The easiest method is the separation of variables, and I've kind of already introduced it, but we're just going to make it more official now. And we'll start out with what their book is calling a separable form. Not used to seeing it in this form, but this is the way the book is presenting it. So you're going to have some function of x plus some function of y times the derivative of y equals 0. Okay, so I mean, it may be in that form, but the main idea is that you're capable of getting something like a function of y on one side dy, and then a function of x on the other side dx. Okay, so this is kind of in my opinion, kind of how you would view it. It's not always possible to separate it. So there's that. So anyways, one thing that the book doesn't really talk about, and even the differential equations book we use doesn't really talk about, is checking for trivial solutions, real solutions. And it's just one of those issues that you'll probably run into eventually, and I want to get it out of the way. And this kind of question, you're kind of able to get the form dy over dx equals some function of x times some function of y, which is I know I'm using kind of the same variables, but you can kind of see it here. You could just divide both sides by n of y, divide both sides by dx, and you could put it in the form m of x all over n of y, which is basically going to be some function of y. Even though it's a reciprocal, it's still some function of y. There's only a y variable in it, times some function of x. Okay. Anyways, to find the trivial solutions, what you're doing is you're looking for where you could plug something in here that would cause the this side to equal 0. So basically, if you find this particular y, I'll call y sub 0, such that function of y equals 0, then the solution, so we could call it y equals y sub 0, is a solution. Okay, and I know it's kind of hard to understand what I'm talking about because I'm kind of talking in generalities, but we can give you some quick examples, right? So example, the exponential growth, the differential equation for exponential growth is clearly one of these types. There is no function of x on the right-hand side. That's okay, though. That means just m of x is equal to 1, and n of y is equal to y, right? But and we notice that if we let y equal 0, then that right-hand side just becomes 0. So that becomes a solution. So we note the right-hand side is 0, and hence this means y equals 0 is a solution. Okay. Putting it more into the kind of illustration or the kind of introduction I was presenting there above, you may see stuff like this. So I don't know, k minus y times x squared. Okay, so clearly here is my function of y, here is my function of x, and solution. What is a solution? Well, if you plug k in for y, if y equals k, then this function of y, k minus y, will equal 0. So if you plug k in for y, you get k minus k, which is 0. So y equaling k is a solution. And I know I'm abusing the letter y. Usually they'll give you a different variable for solutions, like u is a solution. So it's not. Okay, so let me just give you maybe another example. dy over dt equals x over y. Now this guy doesn't have a trivial solution because, I mean, surely if you put in y equals 0, it's like you have to be careful though, right? Because the function of y is not just y, it's 1 over y. If you put in 0, it's undefined, it's not 0. So it really needs to be 0 here. And in other words, I would say there was no trivial solution. Okay. Let's see if I can find one maybe in the notes here. Of course, they're not going to give me one. Yeah, here's one. So another example, dy over dt equals x times the square root of 1 minus y squared. And here you got two trivial solutions, right? So you could have, so the trivial solutions, you can have y equals 1 or y equals -1 as solutions. So, okay, but it's not really going to come up. I just, sometimes I worry about these little sort of minute details. I'm especially worried because I know the book we use at Tri-C, I forget who writes it, but the book we use, they don't go over this, but they kind of expect you to know it somehow, and it's one of those, nobody's going to teach it to you, so I better teach it to you. So hopefully that takes care of that. Okay, so that it's really not an issue for us. It's just kind of becomes a mystery if nobody shows you. So anyways, let's look at some examples, some other more normal examples. Here we have x squared plus 5y dy over dt, or dx, I guess, equals 0. With regards to trivial solutions, this guy doesn't really have any. If you were to get it into the, the dy over dx, you'd have to move stuff around. You'd end up with x squared, negative x squared over 5y, and so there's no trivial solutions. But like I said, it's not really an issue for us at this point. Let me get my markers so I can actually draw here. Okay. Okay, so here is a separable equation. I want to get all the y stuff on one side, all of the x stuff on the other, so I got negative x squared. One other detail that I kind of would want you to deal with is always push or put or divide or multiply the constants on the right-hand side. I mean, sometimes it doesn't matter, you can get away with it, but for particular weird differential equations like that, especially the exponential growth equations, if you don't put it on that other side, you get into a world of hurt if you're not good with exponential equations. Like a lot of students really don't have that kind of experience. So I would say here, put the constant on the right-hand side. In other words, move that 5 over to the other side. So you'd end up with negative x squared over 5. Okay? And then, separate completely, get that dx over. So you have y dy equals negative x squared over 5 dx. Technically, what you're doing is integrating both sides with respect to x. Okay? Just like you would square both sides or add something to both sides. You're doing the same thing on both sides, but just for the sake of kind of simplicity and kind of, I don't know why they do it, honestly. They separate in this way. Okay. Okay. So, anyways, we've got it separated, and on the left-hand side, power rule. Technically, there is like another constant over here, so then there'll be x cubed over 15 plus some other constant. But what you're always going to be doing is adding this constant to the right. So again, it's push the constant stuff over to the right, you'll end up with y squared over 2 equals negative x cubed over 15 plus c2 minus c1. You're going to replace this with just a general constant, because this thing represents all, its range. If you were to think of C2 and C1 as any real numbers, the range of this thing is going to be all real numbers. Okay, so you could just replace that with a big C, x cubed over 15 plus c. And this would be a perfectly reasonable answer. Like if you put it on a test or something, I'd be happy with it. Some teachers will try to convince you otherwise. Like they want you to get rid of all the constants for one thing. You know, okay, so here, this is fine for me. I'm not high maintenance. Fine for Mr. Stroop, okay? But if you're a book publisher, you probably want to get rid of the fractions. So one thing they're going to do is multiply through by 30, right? So you'd end up with 15y squared equals negative 2x cubed plus technically 30c, right? But again, you know, the range of 30c is just going to be all real numbers. So we're going to replace that thing with a constant, big C. And you think of this constant as absorbing all other constants. It won't absorb variables, but it will absorb constants. So we'll absorb that in there. And so rewriting again, you have this thing, negative 2x cubed plus just plain old C. Okay. At this point, I would, this is a better answer. It takes less space, but it kind of looks like an equation of a circle, right? So if you remember, the equation of a circle kind of looks like this. So it just depends on what you're used to. You know, maybe you work in a particular area of science that has a lot of these types of equations, and that's kind of how you would write your answer. So it just comes down to what you're familiar with. You're probably not familiar with much of anything at this point, but this, I think, would be kind of the answer you would see in the back of the book. We still did that sort of thing. If you needed an explicit solution, so this is implicit. In other words, it's not written in the form y equals something. If you do need an explicit solution, and I would advise against getting explicit solutions in these cases, but if you do need one, what you need to do is solve for y. Okay, so you'd end up having to go back to this form and then divide everything by 15. C over 15 is just going to become C again. And then take the square root on both sides. You have to be careful to keep that C inside the square root, and there's a plus or minus involved. So that C is on the inside with a plus or minus. Okay. So I kind of avoid this kind of form, especially when I'm dealing with square roots. When we were dealing with the exponential growth and decay, we did go after the explicit form. But usually when you have one of these plus or minus things popping up, I would just avoid it. So for us, I would say avoid in this case. But it's up to you, and you know, your teacher in the future may have different opinions. They may be specializing in differential equations or something. I don't know. So anyways, let's move on. I think we beat that to death. And look at this guy. That's my cursive letter R, and that's my cursive letter S. I don't know if there's any among you who do not use cursive letters anymore. Okay, this guy should look rather familiar. In particular, it is the exponential growth. It's just with weird variables, right? So we're going to separate, bring the R to the other side. I have 0.75 ds. Integrate both sides. And over here, ln, absolute value of R, equals 0.75 s plus c. Exponentiate both sides, absolute value of R equals e to the c, e to the 0.75s. Drop the absolute values, plus or minus e to the c, e to the 0.75s. And finally, we can replace this thing, okay, with a big C. So R equals C e to the 0.75s. So in this case, it's mandatory to get that explicit solution, this R equals something. If you left your answer right here, you are in a world of hurt, in my opinion. Try again, right? Say no. Do not leave it here. Even though that's an implicit solution, do not leave your answer like this. That's bad news. Everybody's going to make fun of you, okay? No. This over here is your solution. It's well known. It's the exponential growth formula. Everybody should know it. And let's move on. Okay, so that's finding general solutions to separable differential equations. Let's move on to finding particular solutions. So, particular solutions to separable. Okay, so the first thing you're going to do is find a general solution. And then you're going to use the initial conditions to get your answer. Basically what you're doing is solving for C. Find C, right? So this big C over here, in this previous problem, you have R and S, and then you'll be able to solve for that C. In this problem, you would have X and Y, and you can solve for C. So all you need is a point, okay? This initial condition to solve for C. Okay, so let's take a look at this type of problem. Here we have something in separable form, and they give us this initial condition, y of 1 equals 9. Okay, so you want to separate, so I have square root of y, y prime equals square root of x. Move the dx to the other side because you know y prime is just dy over dx. Rewrite your exponents. And then we can exponentiate, or sorry, integrate, do power rules. I'm going to get rid of that constant because those fractions are just nasty. So multiply everything by 3/2. And of course, it'll technically be 3/2 C, but C will absorb that constant and you'll just have a big C. So at this point, I would probably use that initial condition. You may want to rewrite this so it kind of looks like an equation of a circle. Or maybe a hyperbola or something. And then I'm going to put in the initial condition, so I'm going to have to rewrite this. Okay, so y of 1 is 9. So the thing in here is the x, and then the 9 is the y. Okay, so we have 9 to the 3/2 minus 1 to the 3/2 equals C. 9 to the 3/2, how do I do that again? So you could rewrite this as 9 to the 1/2 cubed, right? 9 to the 1/2 is 3, and then 3 cubed is 27. So 27. 1 to any power is 1. So my C value is going to be 26. And then I could write up my particular solution then. Y to the, did I screw something up? Did I lose a negative? I lost a negative there. I apologize. There should be a negative right here. Then that'll be negative. This will be negative. This will be negative. And then this will be positive. And then this will be positive. This will be positive. This will be positive. Finally, this will be 28. If I can get my pen to work. Sorry about that. So finally, my particular solution, 3/2 plus x to the 3, y to the 3/2 plus x to the 3/2 equals 28. Okay. Okay. Let's do one more of these, maybe one that looks a little more intimidating. Okay, so in this case, again, it's separable. So I'll go y times the square root of 1 minus x squared y prime equals x times the square root of 1 minus y squared. Get all the y stuff on one side, the x stuff on the other, so you're going to end up with y all over square root of 1 minus y squared dy equals x all over pretty much the same thing, right? 1 minus x squared dx. Okay. Integrate. Going to need u subs on both of them. It'll be the same u sub. I'll just use different letters. On the left, I'll use u. On the right, I'll use z. Okay, so you're going to let that be the 1 minus y squared and the 1 minus x squared. du is negative 2y or 2x dy. And then dy is negative du over 2y. Let's box that chunk off. So we have y all over the square root of u times negative du over 2y. On the right, I'll go with z variable, so x all over the square root of z times negative dz over 2x. Okay. Simplifying, factor out a negative 1/2. Rewrite 1 over square root u as u to the negative 1/2. U. On the right-hand side, the same sort of thing. And then negative 1/2 u now to the positive 1/2 divided by 1/2 is 2. On the right-hand side, sort of the same thing. Plus c. And back subbing and simplifying, I get negative square root u is 1 minus y squared equals negative square root of z is 1 minus x squared plus c. And then I like to get it kind of in this quasi circular type equation. So I'm going to move this junk over here. And I'll have square root of 1 minus x squared minus square root of 1 minus y squared is c on the right-hand side. Okay, so I need a particular solution, so I zip up y of 0 is equal to 1. Okay, so y of 0 is equal to 1. Again, this is x, and this is your y, so I say square root of 1 minus 0 minus the square root of 1 minus 1. See, so I'll have square root of 1 minus 0. So that tells me c is 1. And now I have my particular solution at the end of the day. Square root of 1 minus x squared minus the square root of 1 minus y squared equals 1. Okay. Okay. So there's there will be a helping of those in my math lab or WebAssign, whatever we use. Okay. One cool thing about these are the orthogonal trajectories. So if you see the pictures in the book, they look like cobwebs. And basically what you're looking for are two families of curves such that each curve in each family is orthogonal. In other words, perpendicular. So you'll get pictures that, one family will be a bunch of circles like this. And then the other family in this case would have to be a bunch of, straight lines, right? Because all the lines would be perpendicular to all the circles, and what you end up with is kind of a cobweb effect. Okay, so it's cool with respect. I like art and stuff like that. So these things are called orthogonal trajectories. And what they're going to do is give you a family of curves, and you got to find the family of curves that's orthogonal. So you use differential equations. I kind of have a program written out for doing these. First, you solve the given family for C. Then you're going to differentiate implicitly. Then you're going to produce differential equation, a new differential equation. Yeah, nobody's coming to my office hours. But you can always stop by, do a couple of homework problems with me. I'm fine with that. If you have any questions, you can see me during office hours. Anyways, produce a differential equation based off of that, and then you're going to solve to get your new family. Okay, sorry about my handwriting. Okay, so let's look at an example of this. We have a family of exponential curves here, y equals ce to the x, and we want to find a family that's orthogonal. So I solve for c. So to solve for c, I can multiply both sides by e to the negative x. And then I'm going to differentiate implicitly. So I'll have 0 equals the derivative of c is 0. And here I'm going to have to do a product rule. So I'll leave y alone. The derivative of e to the negative x is e to the negative x times negative 1. And then plus the derivative of y is 1 times y prime times leave e to the negative x alone. Okay. Then I have to solve for y prime. So let me clean it up a little first. And this is your quiz question, by the way, as well. So this is your video quiz for 6.3. Okay, it should be going in your second set of video quizzes, 6.2, 6.3, 6.4, 6.5. Okay, y prime e to the negative x. Move the y over y e to the negative x equals y prime e to the negative x. And then you could get rid of the e to the negative x and you just have y prime equals y. So to form a family of curves that are all orthogonal, what you want to do is make sure that it's the differential equation for that family of curves basically has the negative reciprocal of this this kind of, you think of the derivative as slope, right? So if you think back to your algebra days, you knew two lines were perpendicular if the slopes were negative reciprocals of each other. So what you're just going to do is take that formula there, this dy over dx equals y, and rewrite it as dy over dx equals negative 1 over y. So you just flip the right-hand side, make it negative, and then solve that, and that'll give you your family of solutions. Okay, so right, separate it. So I'll end up with y dy equals negative dx. So keep that constant on the right side. Integrate y squared over 2 equals negative x plus c. And then if you want to get rid of that constant, it's y squared equals negative, get rid of the fraction, negative 2x plus 2c, but then you can replace 2c with c. Right, so that is a family that is going to be orthogonal to the given family. So y squared equals negative 2x plus c. Okay, and you could go to like Desmos or something and fool around with it there and kind of look at the things to see if they're orthogonal. Maybe we should do that for fun. Desmosis. I don't know if it plots like a whole bunch. I'm not very good with Desmos, but all right. Here's our curves. Great, I can't see them all. Okay, so y equals a e to the, where's the stupid exponent button, to the x, And yeah, let's get a slider going there. Okay. So it's all these curves you can imagine. And then the other guy, so y squared equals negative 2x plus some b, I guess. We'll add a slider there. And you can see, yeah, they're orthogonal. Let's see if we can play them. They're always kind of orthogonal, yeah. So you have to imagine it like with all the different lines, sort of. I don't think I can do that. This is very quick. But anyways, that's good. I'll see you later. Have a good day. Thank you for watching, and see you next time.